Is there a copy of you somewhere in some other planet watching this video? The life of this person has been identical to yours in every respect. Or perhaps he or she now decides to turn off this video without finishing it while you keep watching. The idea of having such an alter ego in some parallel universes are now all the rage, cropping up in books, movies, and even jokes. Although the idea may seem bizarre and unlikely, it appears to be substantiated by astronomical observations, forcing us to come to terms with its existence. Parallel universes have become kind of a source of confusion, since many forget to distinguish between different types of parallel universes that have been proposed. In this video, I will survey theories involving parallel universes motivated by our understanding of physical laws, which form a natural 4-level hierarchy of multiverses, allowing progressively greater diversity. The key question is not whether the multiverse exists, but rather how many levels it has. Level 1. Beyond our cosmic horizon. Level 1 is the least controversial multiverse type. It is based on the concept that an infinite universe with uniform matter distribution allows for the occurrence of even the most improbable events. This means that there are infinite planets with individuals who share your appearance, name, and memories, as well as numerous regions the size of our observable universe where every conceivable cosmic history takes place. This is known as the Level 1 multiverse. If anything, the Level 1 multiverse sounds trivially obvious. How could space not be infinite? Is there a sign somewhere saying space ends here, mind the gap? If so, what lies beyond it? In fact, Einstein's theory of gravity calls this intuition into question. Space could be finite if it has a convex curvature or an unusual topology. The sensitive data from cosmic microwave background tells us that this is not the case, and infinite models fit the data better. Furthermore, strong limits have been placed on the alternative models. How far away can our duplicate universe be? For this, imagine a toy two-dimensional universe with space only for 4 particles. Such a universe has 16 possible arrangements of matter. If more than 16 of these universes exist, they must begin to repeat. In this example, the distance to the nearest duplicate is roughly 4 times the diameter of each universe. The same argument applies to our universe, which has space for about 10 to the power of 118 subatomic particles. Roughly, this gives the estimate that your closest identical copay is about 10 to the 28th meters away, and identical universes are about 10 to the 118th meters away. The framework of Level 1 universe is used routinely to evaluate theories in modern cosmology, although this procedure is rarely spelled out explicitly. When cosmologists say they have ruled out the spherical model with 99.9% confidence, they really mean that if this model were true, fewer than 1 in 1,000 Hubble volumes would show spots as small as those we observe. Level 2. Other post-inflation bubbles. The key difference between Level 1 and Level 2 multiverses is that different universes in Level 2 can have different physical constants, types of fundamental particles, and space-time dimensions. However, it's important to understand that both levels are governed by similar laws of physics. Those other multiverses, which constitute a Level 2 multiverse, are predicted by the currently popular theories such as chaotic eternal inflation and string theory. The phrase chaotic eternal inflation refers to what happened just after Big Bang. Space as a whole is stretching and will continue doing so forever, but some regions of space stop stretching and form distinct bubbles, like gas pockets in a loaf of rising bread. Infinitely many such bubbles emerge which form a distinct universe. Those bubbles are more than infinitely far away from Earth, in the sense that you would never get there even if you traveled at the speed of light forever. The reason is that the space between our bubble and its neighbors is expanding faster than you could travel through it. The Level 2 multiverse is much more diverse than the Level 1 multiverse, as the bubbles not only vary in initial conditions, but also in immutable aspects of nature. According to prevailing physics theories, the dimensionality of spacetime, the qualities of elementary particles, and many physical constants are not inherent to physical laws, but arise from symmetry-breaking processes. For example, it is believed that space once had 9 dimensions, with 3 taking part in cosmic expansion and becoming the observed 3 dimensions. The other 6 dimensions are either microscopic with a donut-like topology or confined to a 3-dimensional surface in the 9-dimensional space, rendering them unobservable. The fine-tuning of physical constants is crucial for our existence. Small changes in their values would result in a vastly different universe, one that likely would not support life as we know it. For instance, if protons were 0.2% heavier, they would decay into neutrons, destabilizing atoms. If the electromagnetic force were 4% weaker, there would be no hydrogen or normal stars. A weak interaction would mean no hydrogen, while a stronger one would prevent supernovae from seeding space with heavy elements. If the cosmological constant were much larger, the universe would have exploded before galaxies could even form. The Level 2 multiverse theory predicts that physicists will never be able to determine the values of these constants from first principles. They will merely compute probability distributions for what they should expect to find, taking selection effects into account. The result should be as generic as it is consistent with our existence. Level 3. Quantum Many Worlds. The Level 1 and Level 2 multiverses involve parallel worlds that are far away, beyond the domain even of astronomers. But the next level of multiverse is right around you. It arises from the famous and famously controversial many worlds interpretation of quantum mechanics, the idea that random quantum processes can cause the universe to branch into multiple copies, one for each possible outcome. Quantum mechanics explain the atomic realm, but its meaning is still hotly debated. The theory introduces wave function, which evolves unitarily over time, but connecting it with observations is tricky. In the early 20th century, physicists postulated wave function collapse to explain observations, but it made the elegant theory non-unitary and kludgy. Over the years, many physicists have abandoned this view in favor of one developed in 1957 by Princeton graduate student Hugh Everett III. He showed that the collapse postulate is unnecessary. Many world interpretation of quantum mechanics predicts that one classical reality gradually splits into superpositions of many such realities. Observers subjectively experience this splitting merely as a slight randomness, with probabilities in exact agreement with those from the old collapse postulate. This superposition of classical worlds is the Level 3 multiverse. As strange as this may sound, the exact same situation occurs even in the Level 1 multiverse. You have evidently decided to keep on watching this video, but one of your alter egos in a distant galaxy turn off the video after watching the first minute. The only difference between Level 1 and Level 3 is where your doppelgangers reside. In Level 1, they live elsewhere in good old 3-dimensional space. In Level 3, they live on another quantum branch in infinite-dimensional Hilbert space. Level 4. Mathematical Universe. The initial conditions and physical constants in the Level 1, Level 2, and Level 3 multiverses can vary, but the fundamental laws that govern nature remain the same. Why stop there? Why not allow the laws themselves to vary? How about a universe that obeys the laws of classical physics with no quantum effects? How about time that comes in discrete steps, as for computers, instead of being continuous? How about a universe that is simply an empty dodecahedron? In the Level 4 multiverse, all these alternative realities actually exist. This ultimate type of parallel universe opens up the full realm of possibility. Therefore, in Level 4, any mathematical existence corresponds to a physical existence. Equations, and more generally, mathematical structures such as numbers, vectors, and geometric objects describe the world with remarkable verisimilitude. In a famous 1959 lecture, physicist Eugene P. Winger argued that the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious. Conversely, mathematical structures have an eerily real feel to them. They satisfy a central criterion of objective existence. They are the same no matter who studies them. A theorem is true of whether it is proved by a human, a computer, or an intelligent dolphin. Contemplative alien civilizations would find the same mathematical structures as we have. Accordingly, mathematicians commonly say that they discover mathematical structures rather than create them. Therefore, a mathematical structure is an abstract, immutable entity existing outside of space and time. If history were a movie, the the structure would correspond not to a single frame of it, but to the entire videotape. In summary, Level 1 multiverse is a region that lies just beyond our cosmic horizon. It has the same laws of physics, but different initial conditions. Such a multiverse is expected since our current observations from cosmic microwave background suggest space is infinite with ergodic matter distribution. Level 2 multiverse has the same fundamental equations of physics, but perhaps different constants, particle types, and dimensions. We can expect such universes if we have the assumption that chaotic inflation occurred during the Big Bang period. Level 3 has features similar to Level 2, but arises from the unitarity of quantum mechanics. In Level 4, even the fundamental equations of physics can change, and each mathematical existence corresponds to the physical existence.